Last week, we learned about vanilla generative adversarial network, which consists of minimax GAN or GAN and non-saturated GAN or NS GAN or DC GAN with some convolutional architecture. You can find many GAN code in GitHub. You can find in PyTorch tutorial. So today I will explain Wasserstein GAN. So what you will learn today is known problem in the previous GAN, which is GAN and non-saturating GAN. And we will evaluate what kind of definition from probability theory that being used by the GAN who have problems. And then I will introduce optimal transport and then introduce Wasserstein GAN, which is another GAN with divergence definition from the optimal transport theorem. Okay. So GANs is very known problem in GANs is vanishing gradient and mode collapse. Yeah. So even if you use non-saturating GAN, when you change the objective from minimizing and maximizing to max stochastic gradient descent, you still have commonly found these two problems. Okay. And also another problem in GAN is basically even the idea coming from Nash equilibrium that during the training we want to reach Nash equilibrium, but the algorithm itself is gradient descent. We never found Nash equilibrium. There is a lot of paper about that, but there is no proof that that is Nash equilibrium. But many prove that what we are looking for is saddle point. Saddle point is the position where in stochastic gradient descent ascent, where it's also minimum, it's also maximum at the saddle point. So let me start with the mode collapse. So mode collapse happen when you train GAN and then it not generating diver samples. It generate the same sample, same over again. So this problem known in all GAN before. And another problem is vanishing gradient, where you train GAN and suddenly all the discriminator loss and generator loss is not decreasing, but is flat. It's no learning anymore. Means that there is no gradient to learn. Okay. So how people handle this problem? So many methods, various methods and techniques they propose. There is heuristic techniques. They change the architecture. They claim that my GAN better than yours. They tune the hyperparameters. They normalize every layers. Huge amount of techniques here. Okay. Some of them we are still using until now. Some of them is no longer relevant. But the problem with GAN at that time, there's so limited theoretical study regarding GAN itself, like loss function formulation or regularization. Even one paper from Google in ICML 2019, this is all Google paper. They said then we don't have to worry about other things as long as we have many computational power. Train GAN, it must be converged. Okay, so many debates. Every week we got a lot of papers. At that time, I took my PhD in this topic, so it's very frustrating period where GAN is explode. So many GANs, yeah. But after Wasserstein GANs introduced, people have more better understanding regarding the theoretical based perspective of GAN. Okay, so what really happened is, let's say I have two samples, dogs and fish, And I said dogs is generated by probability distribution P, and fish is generated by probability distribution Q. So in mathematics, two collection of samples, let's say I say X and Y for dogs and fish, from unknown distribution P and Q, yeah. If I want to define the distance of P and Q from the samples, okay, I repeat, I want to define the distance of P and Q with its samples only, because P and Q is unknown, okay? There is two methods. I use the left side here, P minus Q, or P multiplied by Q to define the divergence or distance. So in mathematics, the left side, we call it integral probability matrix. If you learn deeper on mathematics theorem, this is IPM theorem, that the distance of two probability distribution PQ, we can find the distance by its samples. That's why here you find expectation value from the samples, not because we don't know P and Q. Another side is F divergence, okay? F divergence is probabilistic. IPM mostly coming from optimal transport theorem. And F divergence come from probability theorem, like Kullback-Leibler divergence, or KL, or Jensen-Shannon divergence, which is the symmetric version of Kullback-Leibler divergence. Another divergence like Hellinger or Pearson-Chi is actually F divergence. And theoretically, these two, IPM and F divergence, have a very different characteristic. So F divergence is very simple to compute. However, it has weakness. It's very hard to use F divergence because it cannot metricize weak convergence and no mapping between P and Q, or between the two measures, okay? On the other side, MMD have a very good sample complexity, geometry property, can metricize weak convergence, it can have mapping, but at that time, the computation is very costly. So people start GAN on the right side using KL. That's why they have found many problems. So in F divergence formulation, sometimes we call C divergence from Caesar. It's actually P multiplied by Q in term of probability. We can say is if the is semi-continuous function, it's becoming like this. Okay, you don't have to memorize the math, but this is known in probability theory that C divergence usually defined by Kullback-Leibler divergence and Jensen-Shannon divergence. GAN and NS GAN is based on KL divergence. The problem with F divergence is really not stable, okay? Because it cannot metricize weak convergence, okay? But people know this lately, and they try many GAN, but some GAN is who are still using KL divergence is no longer being used now. So there's a lot of problem, but this theorem of weak convergence proves that F divergence is not really good. But some GAN now still use F divergence, but it's not really good as IPM, or integral probability metric. So NS GAN, if you notice in the last lecture, last week lecture, is using actually GS divergence, which is the symmetric version of KL divergence, can be defined as a combination of KL divergence. So it's a symmetric of version of KL divergence, or Kullback-Leibler divergence. Integral probability metric is a different definition, but is coming actually from optimal transport theorem. Okay, let's go deep into this theorem. So there is many metrics for distance in IPM, like Dudley, Kolmogorov, yeah. Lately, there is a Kolmogorov network proposed by Microsoft Research that they propose multi-layer perceptron that have a better interpretation called GAN, GAN, yeah, in 2024. So that's coming from IPM, like Kolmogorov, Sobolev. Today we will learn about Wasserstein distance. Okay, so this is better alternative than F divergence. So Wasserstein distance start from this theorem. It's very interesting theorem because the founder of this theorem is Mange. Yeah, is a general of logistic in Napoleon Bonaparte army. So as a logistic general, he addressed a problem. If he wants to build a building, yeah, he have to move some soil or from one location to another location. And let's see, the original location is mu and destination is nu. You can see this as a discrete or continuous transport problem. Okay, so the question is, find a coupling. Coupling mean like a path. Find coupling or path. So you can minimize total cost of moving mu to nu, yeah, mu to nu. If you know the unit cost C of the unit mass of the soil. So this problem is started in 1850. So the initial formulation is like this: is find the minimal cost of moving mu to nu. Yeah. So this theorem is has many application optimal transport theorem in economic. And until now, we use it. And Kantorowicz, if I'm not mistaken, his Nobel Prize is revised the Munger definition of optimal transport by relaxation of the theorem. Means that we don't have to have one-on-one mapping of unit mass, but he make it more flexible or make a relaxation. So he changed the definition W mu nu as finding minimum path or minimum total cost of this integral. Okay, so based on Kantorowicz definition of optimal transport, we can deduct P Wasserstein distance. Okay, if the unit cost is C x y, this is the unit cost of moving one unit of mass from mu to nu, yeah, can be described as a function d or distance with order p. So what we so-called P Wasserstein, yeah, is root by P, W1 multiplied by P is called P Wasserstein distance. Okay. So from optimal transport, we define a distance called P Wasserstein distance. So you can find many libraries to draw something like this. So this is like illustration of the idea. So let's say mu and nu is continuous value or discrete value like this. So what we are looking for is P, the path that if I total the total cost using this path, then I get the minimum total cost of moving mu to nu or alpha to beta in this case. Okay. we can view Wasserstein distance in discrete scenario or in continuous value scenario. Okay. So based on Kantorowicz's definition in 1942, we have this definition, which is the relaxation of Mange initial definition of optimal transport theorem. And next, how we use this in GAN. So let's say from latent space noise generated by non-random noise like Gaussian, we call it Z. Okay. And generator, we call this generator as a push forward function G theta. G theta here is generator with weight parameter theta. Okay. So from Z, we put it into generator, yeah, and then it will generate mu theta. Why mu theta? Because it has push forward function with parameter theta. Okay, so we can say model measure or model probability distribution is mu theta. With analogy of previous analogy P and Q, you can say that mu theta is the P. Okay. And then from real data, we only have the sample. We call it nu, the red color here. So we say the distance between mu theta, which is parameterized by theta, and the nu is defined by loss between the model and data. So loss is defined as a function of mu theta and nu. And here, for the loss, we can use Wasserstein distance. Okay, so we say the distance between two distribution, mu theta and nu, is defined by Wasserstein distance. So based on this formulation, we can reformulate the Wasserstein using Wasserstein distance that GAN should be minimized and maximized on expectation value of this one. It's much more simple, yeah. But to make sure that this happen, we have to make sure that we have first Lipschitz constraint. Okay. What is Lipschitz constraint in mathematics? Lipschitz constraint is a condition to make sure that the function is continuous. Okay. So Wasserstein formulation defined by this with first Lipschitz constraint. So initial GAN formulation looks like this. Yeah, it has a better theoretical background from optimal transport, and the cost function, the divergence is defined by supremum of expectation value of fx. Okay, so we call it fx here as a critic function. In previous GAN, we call it discriminator network. But in Wasserstein GAN, we call it critic function. Some people are still using discriminative function, not critic function. But in the original paper of Wasserstein GAN, it changed to critic function. And this critic function represented by neural network. And this neural network have to be first Lipschitz constraint. And many methods they're using until now to make sure that the discriminator as a first Lipschitz constraint. Okay, original Wasserstein GAN just using simple weight clipping, yeah, in the algorithm. So after they found this GAN and then test again to Wasserstein GAN model, Wasserstein GAN show better convergence. There is no mode collapse. There is no vanishing gradient compared to GAN and NS-GAN. So if we compare the concept in Wasserstein GAN, we still have generator like in GAN or NS-GAN. What is the difference here? They call the discriminator, which is implemented as a neural network as well, as a critic function. Okay. And what else difference here? We no longer use logarithmic or entropy based from Kullback-Leiber divergence. Okay, but we use simple like this. As you can see, assuming f is the critic function or discriminator, so we just we just sum all of the output of the discriminator from the real data and from the fake data. Okay, very simple computation. So in terms of computation, should be faster than NS-GAN. Okay, and it has a good result because he's used the better objective function. Yeah. So critic function here, sometimes we call discriminator, but if you use WGAN, usually you say critic function, not discriminator. Okay. So the definition of the optimization is like this. We maximizing the problem to find the F. Yeah. We still use stochastic gradient descent 2 times. This is the paper submitted by Martin Arjovsky. I think he is now in OpenAI. So first, assuming the generator parameter is theta, okay, while theta is not converged, iterate, update the critic function or discriminator many times and critic times by sampling from rich data, the batch from real data, the batch from generator, and then compute this loss function, and then update the parameter using RMS probe, and to make sure that the critic function have Lipschitz constraint, implement weight clipping here. After n critic time, then sampling update the generator parameter theta, okay, using RMS probe. So when WGAN exists and people make it as change the network using DC GAN, it shows that it has better result compared to previous GAN that are using F divergence. Okay, and then many other papers come explain that we can use more better regularization like gradient penalty instead of weight clipping. We can use spectral normalization. Yeah, so WGAN with gradient penalty from Guljarani is improving WGAN by adding gradient penalty in the objective function. Okay, if you can see here, the objective function is very simple. Just minus the expectation value of the output of discriminator or critic with the real data. So WGAN GP algorithm is just adding some penalty aspect, is a kind of regularization to make a better training. And the result, this is the result of WGAN GP. But I rarely use this. I prefer the approach from Miyato, from spectral normalization idea from ICLR. So spectral norm, instead of adding the objective function, changing the objective with gradient value, it has spectral norm on the architecture level. So spectral norm stabilize the training of the critic function or discriminator by normalize the weight matrix. Okay, the purpose of this normalization is to have Lipschitz constraint to make the output, the function is smooth, yeah, is continue and smooth. Okay, that's what we call Lipschitz property. Okay, so it's just like having a function, and then each layer you implement this function to make the spectral norm GAN. Okay, it's more stable. The result is better than WGAN GP. Okay, and then many other people change again make some proposal like this, but this is rarely used. Yeah, from this paper, Wu et al. Okay, so we can say that WGAN with spectral norm is better than others. So That's all for WGAN. Many GAN now is still not using Wasserstein GAN or WGAN. But I believe if you have previous architecture using Jensen-Shannon divergence and then you change to WGAN, you will have better result. Okay. You can try to train your GAN, find WGAN code in PyTorch tutorial or GitHub. There's a lot of code there. If you use ChatGPT, make sure that you understand the code because I'm worried if the result is not as good as the original paper. So find out better sample code for WGAN, which is exists many in GitHub. Yeah, and you can also implement spectral norm GAN, which is WGAN with some kind of regularization. Okay. So your homework for this week is try to implement your first Wasserstein GAN, which is based on optimal transport theorem. So this will open your horizon that when we define objective function in neural network, we can see from different aspects, from probabilistic or from optimal transport aspect. Okay, especially when you have objective that have to compare two different samples with two different probability distribution that generate the sample. Okay, that's all from the theoretical and fundamental aspect of Wasserstein GAN. And before I give to JC for code demo, if is there any question from you, please. Okay, if no question, then please, Jesse, continue to give demo of Wasserstein GAN.
Let me share my screen first. Okay. As usual, we will be trying to implement Wasserstein GAN using ChatGPT in Google Colab. And if you already have your ChatGPT and Google Colab opens, you can start prompting to recreate the WGAN. For the first prompt, we will ask ChatGPT to implement. Let's give some context. Right? New cell in Google Colab. For the first implementation, we will try to implement the loss function first. To implement, let's see if I can type this out. Wasserstein loss function using we'll be using PyTorch for this. Using PyTorch. Okay, as you can see, the Wasserstein loss function is just the mean of y true times the y pred. Let's see, 1 second. Let's try to regenerate first. Okay, this is the example of Wasserstein loss. It is the mean of real data minus the fake data. It's giving us some example to use. We can do that. Let's try and copy this code on Google Colab. Let's see, it's still connecting to the server. And I will copy this prompt first. Okay, this is the result of the functions with this example data. And the calculation with Wasserstein loss function is this for this example. After we implement the loss function, we can try to design a generator network for WGAN, like almost like the same as before. We will try to design the generator network and the discriminator. On this case, it will be called critic network, and we'll be combining those two to create a single WGAN model. Okay, so after the loss function, we will try to write a new cell to design a simple generator network vector architecture for the weekend. See, it's creating class and forward function, and it's giving us some example usage for this generator class. Okay, so it initializes the generator class, and after we generated the generator class, we can create the critic one. As the same before, we can accept T to write a new cell to create a critic. So we critic and network for the weekend. See how ChatGPT made it. As you can see, it's almost the same with generator, but this one linear value and the forward functions. Oh, this is the forward functions. This sequential of architectures, and this is the example usage for the critic architecture. Let's just copy this code. Oh, I will copy the from first for this one, and also the what's it called, the critic network. This is the critic network. Okay. Like before, we will combine the two architecture to a single WGAN model. You will ask GPT to write a new cell to combining the what's called the generator and critic to make a single WGAN model. Let's see. Oh, it creates the previous generator and critic class, and it's the WGAN model, and it asks for the generator and critic for, so it's safe. Let's just copy this whole code to Google Colab, and that's it. This should be the whole WGAN model with the generator and the critic architecture. As you can see, this is the example usage. This is initiating the WGAN with the generator architecture as input, and also the critic architecture. Let's see. One second. Put result. Let's see if we can find out why what's named critic and what does it do in ChatGPT. What does the critic architecture do? Let's see. And so the critic is a neural network model that serves as a discriminator in the Wasserstein generative Wasserstein GAN, and the function is to assess the authenticity of the input data, distinguishing between real and fake samples generated by the generator network. So the generator network will generate some fake samples with noise. If you see, let's see, will generate some fake data, and what the critic does is basically let's see, what this one? Oh, this one, and assess the authenticity of the input data and differentiate if it's a real or a fake data. And let's also ask about the sorry the Wasserstein loss functions and on ChatGPT. Oh, what sorry Wasserstein loss function two. Okay, if you ask ChatGPT about the Wasserstein loss functions, uh, this is the definition, also known as the Earth-Mover distance, is a metric used to measure this similarity between two probability distributions. In the context of GANs, the Wasserstein function is deployed to train the generator and discriminator. So to what's called to check if the generator and the critic is doing a good job, we define the loss function, this Wasserstein loss functions, by what's called by calculating the real and fake, the mean of that, the I mean the difference of real and fake, and getting the means. And if it's higher, that should means the difference is higher between what's called between the probability distributions. As you can see, this is the formula, the same as the functions we created before, which is the mean of the critic negative mean of the critic x accent negative mean of the critic x. Critic x represent the output, and the output of the critic network of real samples x. So this is the critic of samples x, and critic x accent represent the output of the critic network of four fake samples x accent. And this is the function for the calculating the mean value. If you can see here, when minimizing the loss functions, the generator aims to generate samples that are indistinguishable from real samples according to the critic assessment, thereby learning to produce high quality samples. So as you can see, generator will generate some fake data, and the critic will differentiate between the real data and fake data, so it can create a more believable or more good, more better or better fake data for the train. As you can see, this is the code, and after that we can train the data as HTTP, write in your cell to train the GAN model. We'll be using this synthetic data for this, so it will then hopefully it won't take too long to train. Synthetic data set. Let's see. Okay, let's check it. Be using 1,000 samples. Oh, it's generating all the network scheme. Let's just copy the necessary parts for this. As you can see, we already generated the class or the architectures for this, and we'll be copying this part of generating the generator and the critic and also the WGAN. And for this one, they are using optimizers Adam, and uh, it is used for the to optimize the generator and also the critic. Let's see. Yeah, and copy this code. Hmm. What I can. Should be generating for now. Okay, this is the generator samples, which is 0.9998. And let's see, this is the long function of the critic and also the generator. So it trains both class or both architecture of the critic and also the generator. Let's see. After that, process processing the generator output. 1 second. Let's see. This one is generating samples. Oh, as you can see here, this is the training process, and this is for the training loops. And for this one, it's generating. I can for generator. Let's see this. What this code does, and the generator. Oh, and we try to generate some samples from our generator class and show some of them. As you can see in below here, this is the generator samples. This is the generator samples is made with the generator architecture class uh, to create some data that mimics the our data set, so it can create much more data from here from our data set. As you can see, this is the result of the generator samples of fake data. After that, uh, we can try to visualize the training progress. Let's see, right result to visualize the training process. Training process. By mapping the generator, sorry, the generator output at different iterations. So we will see if we can visualize the training process by creating a plot in each iterations. Sorry, we will we will try to plot it. It is creating the function again. Hope we can see it better on this one. Shape 2828 is invalid for input size 1. We will do some bug fixing for this one. Also with ChatGPT, and let's see if we can find the line that errors and give it to ChatGPT and also the error message for this. Okay, it creates a new one, new code for this, and let's just copy the code. Hope it's correct for this one. Also same error. Then we will try to debugging again. Same error. Is it the same error? Also on this. It still looks the same on the line 12. seems like the auto-set parameter might not be correctly specified. Let's modify the function to handle the varying output size of the generator. Oh, the output size may be varying, so it tries to modify the functions. See, okay. For this one is try to change the shape for this. For let's see the plot functions. It will show generate samples view from -1 to 28. Let's see if we can try this one. Valid shape. Oh, it must have shape for this. For the generator will give some the ChatGPT some context. This is the example of the generated what's called generated samples. Okay, generated samples. Oh, it will only show the only plot the generated samples. Let's ask them to modify the plotting function to to show and what can I say? Modify the plotting function to show the what did we do before? Let's check. The result of visualize the training process by plotting the generator output. So the generator output at different iterations. Okay, it still does the same with this view. Let's just try. This might not work for this one still, but should hurt to test. Okay, still the same. Maybe the problem is because we are trying to plot it into the space. Maybe we can ask them to plot it with what's called line chart instead on each pillar. Okay. Let's try to copy the whole code instead. And let's hope it works for this one. Might not, but let's see. Still working. Still training. Okay, this is the output, the generator output. And let's see. Maybe we can't really know the output is right or not. Let's see before that. Let's see. How can I compare? Let's see. I can see if the generated output, generator output is called correct or not. You can do visual inspection, just making sure. Subjective, context. Oh, the generated output might be what's called might be differ between data sets, but what you can do is for what's called for generalization, you can try to evaluate with some error we can ask ChatGPT, create new cell to evaluate the the generated samples. Generated samples. Generated. Using what we can do is like inception score. Let's try inception score first. Inception score. Inception score. Okay, it's creating the function for to calculate the scores, and it calculates the mean score and the standard deviation score. Let's try it on this model. Oh, it throws an error. The parameter of something expected value true, but got false instead. This one, let's change it to true. Let's see. I'm sorry for the sound. Second. The shape -1, 1, 28, 28 is invalid for input size of 64. Let's see, fit batch. The error is on this line. Assuming the output size is 28, 28, but the input size is 64. Let's see if we can give ChatGPT some context of this error. And paste this one also. Seems like the reshaping of the generated model batch data before passing it into the inception model. Let's try adjusting the shape. Let's try this one. Okay, still using the false. Change it through GAN. I wonder if data batch, if we can change to like 64 and by 64. Let's try it out of curiosity. Still error, but let's try again. And maybe ChatGPT doesn't. This one doesn't error anymore. But as always, you can always try to what's it called? Reprompt ChatGPT so it can give out the correct answers by giving it some context of the problems and also the data you are having. But on this case, I think ChatGPT doesn't know the output size of this model is. But let's see if we can find it. See, let's view. Let's try to find the fake data batch first. Data batch. So this is the fake data batch. It looks like this. Let's see if we can try a different method for calculating for evaluating the quality of our generated samples. Like, let's see, try a different method to evaluate the generated samples. Maybe it will work. Oh, this one is using the fractured inception distance or FID. Let's also hope this one works. Let's hope so. There might need some debugging for this, but let's try. Still also error. The object aliases has no len. Oh, the real dataset. The real dataset is from the real. Where did it? Name epochs optimizer. Oh, it should have still the real data before we train. Let's see, training loop. What it's train out real data batch. Real data batch is from real batch from the data loader from the dataset. Dataset from real data. Where we get this the real data. Let's check the real data. Oh, it just generating the torch random. Let's see if we can use this one for the real data for this. The data set is this one. Oh, it shouldn't be different, but let's see. Still error, got false. It should be true. This using still inception model. I think that's some difference while it was while it was calculating the what's it called the evaluating the model with some score or the first one is with what's called inception score, and also the second one is fractured inception distance. But you can try on your own and try to debug the code. You can always try to regenerate the samples or give it some context, like because ChatGPT might forget what it had says before. If it has been too long since the prompts it needs. But as always, you can try to debug it with ChatGPT. Okay, that's all from today. Thank you, everyone. Also, don't forget the final. I mean, the midterm exam will be closed this tonight in the midnight on the 12th a.m. And don't forget to submit your assignment and also make it public so can be checked on later. Okay, well, thank you for listening this class. See you next week.